Good afternoon and welcome to Catalan Cymru revision sessions. Now this session will focus on GCSE Chemistry and specifically today the carbon allotropes and electrolysis. And the session will be presented by Mr. Peter Black from Penglai School. Now the session will last around 45 minutes where the teacher will go through the relevant content with you. But if you do have any questions, please use the question and answer section and I will endeavour to answer your questions during the session itself. Now the session will be recorded, with the recording then being uploaded along with any relevant resources to the e-sgol website in the Catalan Cymru area.
Okay, good afternoon. As you've been told, we're looking at carbon allotropes. Then we're going to look at electrolysis, which actually if you go and look on the, I think it was the spring 2021 sessions, or it could have been one of the other sessions, I do go over it, metal extraction. And in there, I talk specifically about the extraction of aluminium, which, as you hopefully know, is electrolysis. So there is a bit of a crossover there. What I've done, though, in this session is I've gone a little bit more into other examples of electrolysis, so you're a bit more competent with the process. And also, and I will make you aware of it, I've covered some of the triple content. So if you're doing double, at some point I'll tell you, you don't need to worry about the additional slides. So let's get started then. So, you know, this is a nice, easy area to pick marks up in your exams. It just is knowing your facts. So we'll start off then with carbon allotropes. And allotropes basically means different forms of the same element. And carbon has lots of allotropes. And specifically two that you need to know about, again covered in another session that we've done previously, so I do recommend you go and look at the other sessions. This one was on bonding. I specifically talk about diamond and graphite. We're going to look at some of these kind of newer carbon allotropes, these newer materials. So here we can see a carbon nanotube, so you need to recognize that structure. And you know, if you look at it, it looks like a sheet of graphite that's been rolled up, although technically that's not what a carbon nanotube is, but that's what it looks like. And you'll see is a really important feature that these carbon nanotubes have, and it's these electrons that are contained within the tube. That gives it some really useful properties. So let's have a quick look then at what the properties are. Like I say, it's like a layer of graphite rolled up, but it isn't actually from graphite rolled up. And the first thing you see here, as I put in the PowerPoint, we've got it's a good electrical conductor, and you need to know why it's a good electrical conductor, and that's obviously these free electrons. Obviously, you know, we can make a link here to this is also why metals are good conductors, because they have free electrons. Graphene as well, as we're going to see in a moment, has these free electrons. I always point out to my students when I talk about conduction, whenever you talk about ionic compounds, do not talk about free electrons. That's the ions. Once they're mobile, they can conduct electricity. There are no free electrons in ionic compounds, but carbon nanotubes do have these free electrons. That gives them really good uses. I say good electrical conductor, and that means future use in computers and paper thin TV screens, also solar cells as well. And the structure as well, this tube structure, these hexagons, makes them very, very strong, but also very light in comparison to similar strength materials. So that gives them particular uses, which we'll look at in a minute. So we've got aircraft, cars, tennis rackets, bikes, and future construction of buildings and bridges. We're not using them at the moment in these sort of things, the buildings and bridges, because they're too expensive to produce, but you know, we're not far off from actually incorporating them into those materials. So you can see here how strong they are, 100 times stronger than steel, but 6 times lighter. All right, so obviously very, very useful for aircraft. A little clip there for you to go and watch as well, if you want to click on that link on carbon nanotubes. You see here, I've just put a little slide in here. One of the things they're looking at carbon nanotubes for is in the development of solar panels and foldable batteries as well. Okay, so very good for batteries, very good for solar cells. Again, you know, these are technologies that are emerging. You see here, I can remember when I first started teaching about nanotubes, which, oh God, a long time ago now. But I can remember reading, oh, well, there'll be flat screen TVs that are paper thin and can be rolled up. And I can remember thinking, yeah, right, that will never happen. Well, it has happened. They're here now. We have these roll-up TVs, also your smartphones, and also in your microprocessors. So, you know, there's something called Moore's law, which kind of determines how small your processors can go, and you know, carbon nanotubes could redefine where Moore's law takes us to. So we can you know, use their ability to conduct to produce these super small, super fast processors. Worth knowing those uses, okay? Because you quite often be asked them. We've also got the use in sports equipment, and the reason they're using nanotubes there is a because they're light, so you know your mountain bike will be much lighter, but also they're very rigid as well. So this is good for, you know, mountain bikes and things like tennis rackets. You get a nice whipping action from them. Golf clubs as well. And then we move on to another type of allotrope, and this is called a buckyball or a Buckminster fullerene. It's named after an architect who came up with a sort of a similar shape in buildings, geodesic domes. And the most common form of the carbon buckyballs or your Buckminster fullerenes is C60. And you'll see here, I mean, the characteristic shapes we see that form these spherical objects are hexagons and pentagons. And this type of the carbon nanotubes and the Buckminster fullerenes, they're a class of material which you call a fullerene. And a fullerene is a carbon molecule that's hollow. All right, so the nanotubes are hollow tubes, and these buckyballs also hollow as well. And we're just going to talk very quickly then about these buckyballs and how they're potentially useful. As you can see there, I've said they're looking at them in delivery of drugs to specific parts of the body. So they can they insert the drug within the buckyball itself, and then they can attach groups. Well, didn't mean to do that. They can attach groups onto the buckyball that when you get to the area that you want the drug to be delivered, they can shine, for example, infrared light through, or UV light, well, probably not UV light, or ultrasound, and that will make the buckyball disintegrate and actually deliver the drug specifically where it needs to go. So you can target drugs to particular parts of the body. At the moment, you know, with chemotherapy, chemotherapy has a devastating effect on the rest of the body, because, you know, it affects the whole body, and you have to use big doses because it has to go around the whole body. This would be a really kind of groundbreaking way of treating cancers. And then, as well as that, you know, buckyballs make good lubricants because of their shape, a bit like marbles. So you can imagine stepping on a ball full of marbles, you'd go flying, and because they're very rigid as well. And also as catalysts. And actually, I saw in a recent paper, it said, well, why are buckyballs good as catalysts? And the reason is, and if you look on the mark scheme, because I'll be honest with you, I had to look on the mark scheme, it states because they have a large surface area. Okay. The other thing about buckyballs as well that you may not realise is they do contain delocalised electrons. And again, there was a similar question. It said, can buckyballs, you know, Buckminster fullerene conduct electricity? And there were two answers. So one answer was yes, and that's because they had delocalised electrons like the carbon nanotubes. The other answer was no, and I'll explain why. And the reasoning was, well, they do have delocalised electrons, but technically they're trapped within the cage, so they can't actually move with the charge, with the current. Okay, so either answer was good. Okay, then the final allotrope. This is graphene, wonder material. It's got off the scale conductivity of both heat and electricity. As you can see there, it's a perfect thermal conductor. And hopefully you'll know if it can conduct heat and conduct electricity, that's probably due to it containing our free electrons again. And this is, you know, again, just incredibly strong material and incredibly light. And it will revolutionise, you know, things, technology. If I was to describe it, I would say it's a layer of carbon. It's a layer of carbon atoms, one atom thick. All right, so it's like a two-dimensional shape. And one of the things that, you know, they're potentially looking for you to talk about a use of graphene would be in this strength and its lightness. So a really good one to do would be like to replace Kevlar in bulletproof vests. And I've also, read about them putting graphene into satellites to kind of protect the satellite from micrometeorites. So it's incredibly strong. So those are your allotropes of carbon, other than diamond and graphite, which you can see in the bonding. So what I'm going to do now is we're going to look at what we call smart materials. So there's a couple of smart materials that you particularly need to know about. There's actually 5. You might see there's only 4 bullet points, but shape memory alloys and shape memory polymers are treated as separate materials. I think having a definition is really important of what a smart material is. So you can see here their properties change in response to changes in the environment. But I think what's really important to say is that it's a reversible change. So if the temperature goes up, it will change to respond to that temperature. When it goes back down to the original temperature, it will go back to how it originally was. So it's quite important to have that definition and to use that term reversibly. So let's look at these sort of materials. Hopefully you'll be familiar with them. And hopefully you know what kind of material we've got here. This is a shape memory alloy. And you need to know or be able to tell the examiner what property changes and what causes that change. So if I was asked about shape memory alloy, I would say they're metals that change shape according to the temperature of their surroundings. What causes that change would be a change in temperature, either hot or cold. And it's worth noting an example. So we have this alloy, it's called nitinol, and it's an alloy of nickel and titanium. And we're just going to quickly discuss the uses of these smart alloys or shape memory alloys. So you can see here, this is, you may not realise it, but braces, actually the metal here, not the clamps, but the metal across here, this is shape memory alloy. It's not just an ordinary metal. As you know, metals are malleable. So if you used an ordinary metal, it would take on the shape of the teeth that you already have. It wouldn't actually have the shape that you want the teeth to become. So your teeth have to be under constant strain. So what the dentist will do is they'll program the shape memory alloy to specifically, pull your teeth in a particular direction, and it will remember what that shape is at body temperature. And when you clamp it into the teeth here, it's constantly saying, well, I don't want to be this shape. I want to go back to this shape that I know at body temperature. So that's how, well, probably a little bit below body temperature. That's why you have a shape memory alloy in your teeth. Fire sprinklers is a good example as well. So you can see here we've got our shape memory alloy, and what we've got here is a hollow glass ball, and this is the only thing stopping mains water from actually coming out of the sprinkler. When this gets hot, this shape memory alloy will expand because it wants to straighten out at a higher temperature. That will smash through your hollow glass ball, and then the water will come out of your sprinkler. And then things like thermostats quite often use shape memory alloys. So, things like, for example, a coffee maker might have a shape memory alloy on, and that alloy will change shape and turn the switch on and off for current to flow and turn your heating pad on. So there's your shape memory alloys. Worth knowing again what the change of their property is, which is shape, what causes that change, which is temperature, and then know some uses. Right, so now we've got our thermochromic paint, okay, and therm obviously refers to temperature, like thermometer, and chroma refers to colour, and you may remember that from year 10 with chromatography, which is separating colours out. So we've got thermochromic paints, and we've got what I would class as what we call novelty uses. So some good novelty uses here are, for example, colour changing wool or paint. Not quite sure why you'd want that. Again, a mug here with a little design on. Again, I would class it as being a novel use. Another good novel use, I don't think I've got a picture of it here, is called a mood ring. So these are mood rings that change colour and tell you whether you're angry or calm or in love. Well, they're not telling you that, they're telling you your body temperature. And you can see that here with what we've got is a contact thermometer. You might see those on fish tanks as well. They just change colour according to temperature. A really good one is a battery test strip indicator. And again, it's worth knowing that one. So if you put your fingers one there and one there, you complete a circuit that gets a little current flowing through this bit of the battery here. with resistance, it generates heat, and the amount of heat changes the colour of this indicator. So that's a really good use. And then we've got another really good use as well. We've got the safety aspects. So we've got a feeding spoon and a bath toy, and you can see here this bath toy is yellow when it's cold, it's blue when it's too hot, it's red. So that's a good way of indicating that something's too hot for the baby. So again, what causes the change? Temperature. What changes is the colour, and know some uses of that. I'll just show you this slide here as well. Oh, there you go. That's the definition of them. Materials with colour change in response to changing temperature of its environment. Should there, though, I should say reversibly change. Okay, so novelty and safety. And well, don't use this one in the exam. It just makes me laugh. I think it's quite funny. These are some urinals in China. I think it's in Shanghai airport, and you can see here I don't know why they've done this, but they've coated the urinal in thermochromic material, and you can see where the urine has come out. It's warm, it's got this red colour, and then as it drips down and cools down, it cools down and correspondingly changes colour. That's quite a strange use of thermochromism. Like I say, don't quote that in the exam. But it's nice to see. No, I don't know if I'll do that. No, don't want to do that. Bear me a second. Right, there we go. Right, so moving on to the next slide. Photochromic. So hopefully you know what photo refers to. I'll give you a clue. Photosynthesis, photograph, photon. It refers to light. So these are materials who reversibly change colour in response to light intensity. That's a nice word to use, light intensity. So where do we use these materials? Well, the best use I've got would be in what we call reactive lenses. And that's a nice term to use, reactive lenses. And these are kind of lenses that, you know, can be sunglasses when it's bright and you step outside, and then when you're inside it's kind of dull. They can be reading glasses. Another use as well, it would be to detect forgeries. Okay, so you can see here under normal light conditions, we've got a photo of the person on the driving license, and then with UV light, we can see additional information. So you'll see that on, for example, driving licenses, banknotes are all good examples. And then another another smart material are our hydrogels. They're also known as polymer gels. And there's not much to know about these materials really, other than that they're well, what's their property? Well, their property is they absorb water. And when I see my pupils say, you know, what's the property of a hydrogel, and they say they absorb water, well, so does tissue paper, so does a sponge. It's how much water they absorb. It's 1,000 times their weight of water. And that makes them useful for things like wound dressings. Wounds need to be kept wet for long extended periods of time. Obviously nappies, because you need to absorb the moisture from the urine and lock it in without it, you know, leaking everywhere. And a really good one is and examiners like asking this a lot, fake snow. So if you add a little bit of, well, quite a lot of water to a little bit of this hydrogel, you'll get this kind of white fluffy powder, and yeah, fake snow. And I've got here shape memory polymer, exactly like the shape memory alloys, but if you've gone onto your C5 unit, you'll know polymers are plastic. So these are plastic that change reversibly their shape in response to change in the environment, and that would be temperature that causes that change. So the best use of that I've seen really is in car bumpers. So car bumpers can be made from plastic, and if you have a little bit of a dent, you don't crack the plastic, you can just pour hot water on the plastic and it will go back to the original shape of the car panel. Not really a smart material then, because remember, smart materials respond to changes in their environment, but they are because they change how much water they can absorb depending on the pH or salinity. So for example, if you make the water more salty, they're not so good at absorbing water. So they'll expel that water. And then if you reduce the salinity, then they'll reabsorb the water. So that's why they're classed as a smart material. And because they're absorbing, they can change how much water they absorb. That will cause them to shrink or swell up. And that means there's a potential use in the future of making artificial muscles, believe it or not, out of these hydrogels. If I'm asked for a use of a hydrogel, nappy, fakes, no. I wouldn't talk about artificial muscles. I'm just throwing it in there for you as a matter of interest. And just in case the examiner ever asked you, you know, which smart material could be used. And that's our smart materials. So now we'll come on to our nanochemistry. So nanochemistry, hopefully you know what a nanoparticle is. These you do need to know what a nanoparticle is. We class them as particles that range from 1 to 100 nanometers. Okay, so it's got to go from 1 to 100 nanometer. A nanometer is a billionth of a meter, which is, you know, obviously very, very small. Remember, a million seconds is something like 11 days. A billion seconds is something like 34 years. So we're talking very, very small scale. And one of the things the exam board want you to know is that when you get down to these kind of scale, these size of particles, materials change their properties. So you can think of materials as being as bulk materials, which is where, you know, every day, where what we see, what we interact with, and then we come down to the nanoparticles. And when we get down to nanoparticles, their properties change. And I've got here a picture of nanogold. Now, you don't need to know about nanogold for your exam board, but it's quite a nice thing to just show you. I've got here a nanoparticle of gold, and each of these little dots that you can see in the picture there is actually an atom of gold. So you can see a nanoparticle still has a fair few atoms in it, as you wouldn't be surprised. This nanoparticle here is looking like it's got a diameter of 10 nanometers or maybe 8 nanometers, so it'd definitely be a nanoparticle. And this is what we call bulk gold. So, you know, a gold ring is a bulk material, and the properties of nanogold are quite different to bulk gold. Okay, so one of the things that's different about nanoparticles is their color. So gold, and it's the way the large surface area is why they have different properties. Gold, for example, has different colors. So you can see here, we can have gold when it's 50 nanometers, appears green in color. When it's 100 nanometers, it's got more of an orangey color. Silver here has got lots of different colors. And in fact, actually, nanoparticles are used in making stained glass. They didn't know they were using nanoparticles, obviously, when they were doing this, but these are the colours that we get in stained glass. It comes from nanoparticles of gold and silver and other metals, I imagine. So we need to specifically focus in on nanosilver. And what is it about nanosilver? Well, nanosilver's antimicrobial. And what that means is it kills viruses, it kills fungi, molds, bacteria. And so it's got some really good uses. So one of the main uses of nanoparticles is it's stitched into clothing. And this is to kill the bacteria that cause body odour. So it's not your sweat that smells, it's the bacteria eating your sweat and then emitting kind of gases like we do through breathing. They emit gases that have an odour. Right, so if you kill the bacteria, your sweat won't smell. Right, so that's a good use. Stitched into clothes. Also, we find it in plasters. If you have a cut and you've broken one of your first lines of the immune system, which is your skin, if bacteria get into that cut, they can cause infection. So if you put nanosilver plasters on, that will stop those bacteria from infecting the wound by killing them. It's also used in hospitals. So it can be used as a sterilising spray. So if you have a particular outbreak of a nasty bacteria like MRSA or C. difficile, they'll spray the ward down with this nanosilver and it will kill those bacteria off. And also I've got here a fridge. So sometimes fridges have nanosilver coatings on the plastic, and that's to stop bad odours building up in the fridge. So you can have bacteria growing on the surface of the fridge and they over time can give off quite bad odour. So if you've got nanosilver lining the fridge, those bacteria can't grow on the surface and cause that smell. And also deodorants. Okay, so you can see here, this has got nanosilver included in the actual deodorant itself. Nanosilver, by the way, is sometimes called colloidal silver. So if you ever see colloidal silver, basically it's nanosilver. Okay. And the way nanosilver works is it gets into the bacteria because it's so small and it stops the enzymes from working. But you don't need to know why it works. You just, I thought I'd put that as a bit of interest. Okay, so we'll just move on. And then another kind of nanoparticle that you need to know about is Nanotitanium Dioxide. And, you know, that's placed into sun cream. And the reason it's placed into sun cream is it reflects UV light. So it stops the UV light from penetrating it, it reflects it off. But what it does allow through is your visible light. So it basically looks transparent. Also, they use it on the coating of glass. So nanotitanium dioxide reacts with sunlight and water to become self-cleaning. So you never have to clean the glass. The glass cleans itself with UV lights from the sun. So all good things worth knowing. Very important though, you know the dangers. And you've got to be very careful how you answer this in the exam. So, for example, some of my pupils have done a mock recently, and in the mock they said nanoparticles are dangerous because they could affect how the body works. Okay, I think you need to talk about the long-term effects. If we knew that these nanoparticles were dangerous, there's no way we'd be allowing them to be put into deodorants. So what we need to be saying here is, if we're asked about the dangers of nano, we need to say that they're so small. We don't even need to say that. We need to say they can easily enter our body and our cells, and we don't know the long-term effects on our health. So don't just say they're bad, because if they're bad, you wouldn't be able to use them. You need to say the long-term effects on our health. We don't know what those are. Also, you can also talk about the effects on the environment. Nanosilver is constantly being washed into river sources on our groundwater, and we don't know what effect that these nanoparticles are having on bacteria, which are obviously essential to ecosystems, for example, decomposing things. There's been links to nanosilver affecting slugs, and you might think, well, great, we don't want slugs. Well, ecosystems need slugs. We have birds, hedgehogs that eat them. So we don't know what these long-term effects of the environment are as well. So we do need to kind of approach with caution. But like I say, again, I think it's quite important to use the term long-term effects. Again, you know, think about where we're putting these things. We're putting them directly onto our skin. So it is potentially quite serious risk there. So that was the carbon nanotubes done, or sorry, the carbon allotropes done, and I've also touched on there your smart materials, and I've also touched on your nanochemistry as well. And those are easy marks, so make sure you're good at those, because then we come on to more difficult stuff. So moving on to electrolysis. So what is electrolysis? Well, obviously it's using electricity to split compounds up into their elements. And you can see there, lysis is quite a common term in chemistry, and you'll come across it if you do it in biology as well. It means to split. Okay, and if I'm asked what electrolysis is, it's using electric current to break a substance down, and that's made up of ions. And the substance we break up has a name. It's called an electrolyte. So whatever you're doing electrolysis on is called the electrolyte. And how does it work? Well, we've got here a beaker, and you can see I've connected up to a circuit, and hopefully if you know your circuits, you'll know that this is a DC circuit, symbolized here as a battery. So you have a positive terminal and a negative terminal, and that's very important for electrolysis. And I've marked here the cathode and the anode, and I'm going to teach you a little way of remembering which is which, because it is very important you know the charge of the anode and the cathode. Okay, so here's our electrolyte. This is what we're going to be splitting up, as I said, and this is how we remember which is which. I tell my kids now to panic when it comes to electrolysis, because it helps remember the anode is positive and the cathode is negative, and that is crucial you know those terms. So let's look at an example then. Now, it's really important here that I'm pointing out, especially for the triple people who are looking at this in a moment, we're looking at molten sodium chloride here, not aqueous. Molten means it's been melted, aqueous means it's been dissolved in water. So when I think of electrolysis, basically what we're doing in electrolysis is reversing what happened when sodium chloride formed. And hopefully you recognise this diagram here. This is a bonding diagram of sodium chloride. And you can see here that this electron originally belonged to the sodium. So the sodium lost an electron to form a positive ion, and the chloride ion gained that electron to form a chloride ion. And what we're going to do in electrolysis, we're going to reverse that. We're going to give this electron back to the sodium, and by taking it away from the chlorine. So it's always worth thinking electrolysis being the reverse of bonding. Okay, so bear with me a second. So here's some sodium chloride. And we can see our anode and cathode. I'm just going to remind you of panic. Positive anode, negative cathode. And there's a rule in science, you may have seen this with magnets, north and south attract, opposites attract, and it's the same with charge. So hopefully you can see which ion's going to go where. So you can see your negative ions have gone to the anode, and our positive ions have gone to the cathode, because opposites attract. And there's another term you need to know here, and it's the term anion and cation. So the ion that goes to the anode is called an anion. So our chloride ion, our negative ions, are called anions, and the ion that goes to the negative electrode, the cathode, is called the cathode. So our positive ions are called cations. So this is why panic's so important. Whatever goes to the anode is an anion, that's a negative ion, and the positive ions are going to go to the negative cathode, so they're called cations. You do need to be able to identify which is which. So I'm just going to have a little pause here, just for you to have a little think about what's going to happen when we turn on our electrical current. What's the anion and what's our cation? Well, let's have a look. So the positively charged ions, the zinc ions, are going to be attracted to our negative electrode, and our negative ions, our anions, are going to be attracted to our anode. Okay. The other thing I'm going to point out to you here is you'll notice with the sodium chloride and this zinc chloride, both times I've said it's molten, and you need to know why it's molten, and it's the same reason why they'll only conduct electricity when molten or dissolved. Your ions need to be able to move, and it's the same for electrolysis. So what we're going to do now is we're going to look at another example. We're going to look at some lead bromide, the electrolysis of lead bromide. Again, you know, panic. We've got our positive anode and our negative cathode. That allows us to then work out our ions. So we've got this negative ion is our bromide ion, Br minus. That's going to go to this anode, so that's our anion, and our positive ion is our cation. So our lead ion is a cation, that goes to the cathode, and our anions go to the anode. Okay, so we're going to talk about oxidation now and reduction. So these are redox processes. Now, before, when I've talked to my students about oxidation and reduction, we initially talk about in terms of the loss and gain of oxygen. We can also talk about oxidation, reduction, and the loss and gain of electrons. And you can use this term here, oil rig, to remind you what it is in terms of electrons. I'm just going to point out to you, it is only for electrons. Oxidation is not the loss of oxygen. Okay, do not use that. Oxidation, when you're talking about oxygen, oxidation is the gain of oxygen and reduction is the loss of oxygen. Keep it separate. Oil rig is only for electrons. So why do we use oil rig? Well, oxidation is loss of electrons and reduction is gain of electrons. Okay, so let's go back to our terms now, and we're going to look at some lead bromide. Okay, so again, we know where these ions are going to go to. Our positive will go to the anode, and sorry, our positive will go to the cathode, and our negative will go to the anode. Okay, and what ions are they? Well, the lead ion is Pb2+. Okay, and as I said to you earlier, what we're going to do is we're going to give it electrons back so it can reform lead metal. So there's our Pb2+. As we know, it's going to go to our cathode. Why? Well, the cathode is negative and the lead ion has got a 2+ charge, and opposites attract. And we're going to turn it back into lead, and to do that, we're going to have to give the electrons back. Remember, electrons have got a negative charge from year 10. So, you know, if you're worrying about what's going on, just think, well, it's positive. I don't want it to be positive. I'm going to give it some negative electrons back. So we give it 2 negative electrons back. And applying oil rig, oxidation is loss, reduction is gain. So oxidation is loss. No, this is gaining. This is reduction. Okay, so it's reduced, gaining electrons. Who's going to the anode? Okay, well, the bromide ion. Okay, so the bromide ion is Br minus. Okay, Br minus. It goes to our anode because the anode is positive. And what we're going to do is we're going to turn it into Br2 by taking away electrons. Now, what I want to realise here, bromine is diatomic, so it's always written as Br2. So I need to reflect that on this side. Okay, at the moment it's not balanced up. So because I've got a 2 here, I'm going to have to double that. So it's become 2 Br minuses and take away an electron from both of them. So there we go, double that to make Br2. And I'm going to take away an electron from both of them. So I have to altogether take away 2 electrons. And we'd say it's been oxidized. Why? Well, it's lost an electron. Well, it's lost, they're losing electrons. Just a little point here then, you can see a diagram or a picture of the electrolysis of some lead bromide. And you can see here the bromine gas is forming. And this will be at your anode. Remember, Br minus, the negative ion is going to go to your positive electrode. Panic, positive anode. So this is my anode. And you can see the bromine forming. And if you're asked about this, you would have to do this in a fume hood. Bromine is a highly toxic gas. So lead bromide would have to be done in a fume hood. And you can see here the lead bromide is molten. That's why it's on a tripod. It's been heated from below. Let's look at our zinc chloride then that we did earlier. So we can see our zinc ions and our chloride ions. So hopefully you know the cathode, it has a, well, let's do it, panic. Positive anode, negative cathode. So we know our cathode is negative and our anode is positive. And now we can work out our cation. So our cation would be the positive ion, the zinc, and the anion would be our chloride ion. And what's going to happen to them? Well, like I say, we're going to reverse what happened to them in bonding. We're going to turn them back into their elements. And to do that, the zinc's going to gain 2 electrons. And the chloride, well, we're going to take away the negative charge. So initially you could say, well, we'll take away that negative electron. But the problem is it's Cl2. All right, so we're going to have to actually take away 2 electrons because we need 2 chloride ions. So we take away an electron from each of them. And hopefully you can see that the zinc is being reduced. Reduction is gain. And the chloride ion is being oxidized. Oxidation is loss. So a little summary there for you to kind of just, you know, emphasize those key terms. And we'll finish off with something like sodium oxide. And again, I'll pause it for you, or you should pause it here. Overall, our reaction is that we're going to split the sodium oxide into sodium and oxygen. And if you think about our ions, or sorry, think about our cathode and anode first, so we'll panic. That's negative. The cathode is negative, the anode is positive. Those are the ions in sodium oxide. So hopefully you know that the sodium ion will go to our cathode. That's our cation. And the oxide ion will go to anode. Okay. And then we're going to reverse what's happened. So we're going to give the sodium an electron back to form sodium metal. And the oxide ion, well, we're going to turn it, we're going to take away those 2 electrons and we're going to form O. But, so 2. That's how we always write oxygen in the equations. So I need 2 oxide ions, not 1. And I'm going to take away 2 electrons from each of them. So altogether, we remove 4 electrons. Okay. Now, I'm just going to talk to you about these equations because technically you can write them like that, but it's not the best way of writing them. This is how we've been writing it so far. Okay, so we've taken away, we've got 2 chloride ions, we've taken away those 2 electrons from it and we form chlorine. Technically, you want to put the electrons over here. Now, don't worry too much about it. I think examiners are fairly forgiving. It's the same thing that you've done there. Okay, all you've done is you've said the chloride ion has had 2 electrons removed and here they are. So that's the proper way of writing it. And if you can get your head around that, then do so. Again, here, you know, we've got the 2 oxide ions and we're going to take away their electrons from them. So there we go. We've removed those 4 electrons. So we end up with the oxygens now without those extra electrons. And that's the better way of writing it. So you can write it like that, but that's a more technical way of writing it. So double award, you're finished. Triple award, I'm just going to cover here a couple of extra techniques of electrolysis. So the first one we're going to do is purifying copper. You can see I've got my anode and my cathode. What's different here though is that anode and cathode aren't made from carbon. They're actually active electrodes. They get involved in what's happening in electrolysis. So what I'm going to start with then is I'm just going to say, well, you know, if we turn on our current, hopefully you'll know that your copper ions will move to the cathode, that gain their 2 electrons that they're missing, symbolised here with the green and the little gaps here, and they would form copper metal. Now, what's going to happen if we do electrolysis on something like copper sulfate is eventually all those copper ions would go, and you'd not have any copper ions left in solution. However, because that anode is made of copper itself, anode is where oxidation takes place. And actually, these are more technical terms for the cathode. So cathode is where you get reduction. Every time you're going to be adding electrons. In the anode is where we remove electrons. And what actually happens in this, because our anode is made from copper, we remove electrons from the copper itself, from the copper anode, and they become copper 2+ ions. They transfer into solution because they're ions, and then we reform our copper. So basically, because your anode is made from copper, you constantly generate copper ions by removing electrons from the copper anode. So that's a little one there. What's eventually going to happen is this will be eaten away, there'll be none of it left, and this will build up over time. We've got our pure copper, which is much better at conducting electricity. Okay, 2 equations there for you then, for the anode and cathode. You see the copper, this is the usual one, just adding electrons to form copper, but the anode, we're taking those electrons away. Remember, we could also write that as being Cu, goes to Cu2 plus the 2 electrons. Electrolysis of water, as you can see here, we've got twice the volume of gas collected to oxygen, and the reason for that is the formula of water is H2O. So for every oxygen atom you collect twice the amount of hydrogen. And you can see here, these are your, the reason that we have that is water actually splits up. Not very much of these ions present in water, but you have the H+ ion and the OH- ion, and they get attracted to the anode and cathode. This is called a Hoffman voltammeter. It just separates those 2 gases out so they can be collected. You can see here, hydrogen's formed at the cathode. Remember, the cathode is negative, and the hydrogen ions here are positive. That's why hydrogen forms there. And you do need to know those 2 half equations, okay? So definitely learn those for your exam. And then finally got the electrolysis of brine, and how much time? Not much time. There's our cathode, there's our anode. And what I want you to realise is brine is a solution of sodium chloride. So we've got various species in here. We've got the sodium ion, the chloride ion, and we've got water. And the thing about water that we said earlier is that water splits up into the H+ ion, the hydroxide ion. So if we turn our current on, hopefully you'll know the sodium ion, the hydrogen ion would move towards the cathode, with the chloride ion moving towards the anode. But what happens here, instead of sodium gaining the electrons, the hydrogen gains them. It outcompetes the sodium at the electrode. And this is to do with the reactivities of sodium and hydrogen. Hydrogen is less reactive than sodium, so it outcompetes the sodium for those electrons. It's hungrier for them. So rather than the sodium gain the electrons, the hydrogen does. Hydrogen's below sodium reactivity series. And the chlorine, well, that goes over to the anode and collects the electrons. And what you're left with in solution then is sodium hydroxide. Okay, the chloride ions become chlorine, the hydrogen ions become hydrogen gas, and you're left with these 2 ions, sodium hydroxide.